Have you ever wondered how your phone unlocks just by seeing your face, or how Netflix recommends a movie you end up loving? The technology behind this magic is machine learning. So, what is it? In one line, machine learning lets systems learn patterns directly from data to make predictions or decisions, without being explicitly programmed for every single scenario. This is a huge shift from traditional software. A normal program follows fixed rules that a developer writes. If the rules need to change, the code has to be rewritten. But a machine learning model is flexible. It adapts and improves its performance as it sees more data. This ability to learn is why ML is everywhere. It's the engine behind powerful search results, the silent guardian in your bank's fraud detection system, the personal shopper in e-commerce recommendations, a radiologist's assistant for medical imaging, and the technology that allows you to talk to your phone with speech recognition. Why is it growing so fast? The adoption of ML keeps climbing because of its incredible scalability. Once you build a data pipeline, tackling a new task is often just a matter of feeding it new data, not completely rewriting the rules from scratch. This makes innovation faster and more efficient than ever before. So how does it actually learn? You can think of it like a universal recipe. First, you need your ingredients, the inputs, which we call X. Next, you need a picture of what you want to create, the targets, or Y. Then you pick a model. This is like your recipe, defining the shape of the answer. You need a way to measure how far you are from the goal, which is your loss function. And finally, you use optimization to tweak your model's parameters until the loss is as low as possible, making your output match the target. Almost every machine learning algorithm you'll encounter is a clever variation of this fundamental recipe. The three big paradigms. Machine learning is a vast field, but it can be broken down into three main approaches or paradigms. First is supervised learning. This is the most common type, where you train the model on data that is already labeled. You show it thousands of examples with the correct answers, like a student studying with an answer key. The goal is for the model to learn the relationship and then make accurate predictions on new, unseen data. Next, we have unsupervised learning. What happens when your data has no labels? This is where unsupervised learning shines. Its goal is to find hidden structures and patterns in the data all on its own, like a sorting hat that groups students by their inherent traits. And finally, there's reinforcement learning. This paradigm is all about learning through trial and error. An agent takes action in an environment to maximize a cumulative award, much like training a dog with treats for good behavior. It's the key to building self-driving cars and game-playing AIs. A closer look at supervised learning. Let's dive deeper into the toolbox for supervised learning. We start with the classics. Linear and logistic regression are often your first step. Linear regression draws the best straight line through your data to predict continuous values, like house prices. It's fast and easy to interpret. Logistic regression adapts this idea for classification, predicting a category like spam or not spam by giving a probability. They are powerful baselines, especially when your features are strong. Then we have tree-based models. A decision tree makes predictions by asking a series of yes or no questions about the data, but a single tree can easily overfit. That's why we have random forests, which build hundreds of trees and average their predictions for a more robust result. Gradient boosting, or XGBoost, takes this even further, building trees one after another, where each new tree corrects the errors of the previous one. These are champions on structured tabular data. Other powerful techniques include support vector machines, SVMs, which find the optimal boundary to separate classes, and k-nearest neighbors, KNN, a simple but effective method that classifies a new point based on the votes of its closest neighbors. And of course, there are neural networks. Multi-layer perceptrons, MLPs, are the foundational workhorse for complex data. And then there are transformers, the architecture that powers models like ChatGPT. They use a mechanism called attention to understand long-range dependencies in data, revolutionizing language, computer vision, and beyond. Exploring unsupervised learning. Now let's explore the world of unlabeled data. Clustering algorithms are key here. K-means is a popular method that groups your data into a predefined number of compact, spherical clusters. For more complex shapes, DB-scan can find clusters based on density. and even identify outliers that don't belong to any group. Hierarchical clustering creates a tree of nested clusters, which can be invaluable for understanding the relationships within your data. Another crucial task is dimensionality reduction. Imagine your data has hundreds of features. Principal component analysis (PCA) is a technique to compress those features into just a few while preserving as much information as possible. It's fantastic for visualization and speeding up your models. For more advanced visualization, TSNE and UMAP can create stunning 2D plots that reveal the intricate manifold structure of high-dimensional data. The power of reinforcement learning. Finally, let's touch on reinforcement learning. This is the frontier of AI, powering everything from robotics to sophisticated game-playing agents. Algorithms like Q-learning and DQN learn the value of taking specific actions in an environment. Policy gradient methods like reinforce and PPO learn the optimal strategy or policy directly. Advanced methods like SAC encourage exploration to find even better strategies, and model predictive control (MPC) allows an agent to plan by simulating future outcomes before taking an action. From model to production, ML ops. Building a model is just the beginning. To create real-world value, you need ML ops, or machine learning operations. It starts with data collection and pre-processing. Then comes model training and evaluation, where you rigorously test your model. Finally, the model is moved into deployment and monitoring, where it serves predictions and is watched closely for any drop in performance, signaling that it may be time to retrain. Real-world impact. The applications of these techniques are transforming every industry. In healthcare, models help read scans and forecast disease risk, acting as a crucial tool for doctors. In finance, they detect fraudulent transactions in milliseconds, protecting millions of customers. And in infrastructure, they predict machine failures before they happen, preventing costly downtime. The future is now. Emerging trends. The world of machine learning is constantly evolving. Here are a few trends to watch. Machine unlearning, the ability to make a model forget specific data, crucial for privacy. Interoperability, tools that let you train a model in one framework and deploy it in another, increasing flexibility. Auto ML, platforms that automate the hard work of building and tuning models, making ML accessible to everyone. Edge and Internet of Things ML, running models directly on devices like your phone for lower latency and better privacy. Agentic AI, creating networks of specialized AI agents that can collaborate to solve complex problems. Responsible and explainable AI, a critical shift towards building models that are fair, transparent, and auditable. Machine learning is more than just a buzzword. It's a fundamental shift in how we solve problems, and it's just getting started.